Okay, so we have seen the continuity of f, that is limit f of x, x goes to a is equal to f of a, then we say that f is continuous at a. Now, if we have two function f and g, both are continuous at a, then f plus g is a function and also that is equal to f plus g, which is a function which we have defined to be f of x plus g of x. Now, this new function f plus g, this is also going to be continuous at a if both f and g are continuous at a. F minus g is also going to be continuous function at a. Now, alpha f, alpha is any real number. So, alpha f, recall that this is the function which is alpha times f of x. Now, this is also going to be a continuous function at a. F and g both are continuous at a, then f g is also going to be continuous at a. Now, f by g, if g of a is not equal to 0, if g of a is not equal to 0, then f by g is also continuous at a. Remember that if g of a is not equal to 0 means, that means what we are going to get is that the limit g of x goes to a is equal to g of a. That means, there is a neighborhood in which we are not going to get that this is going to be equal to 0. So, all this proof is going to follow just by the limit what we had done this, the limit of f of x plus g of x, this is equal to limit of f of x plus limit of g of x if both the limit exist, and in this case the continuity you are being guaranteed that the limit exists and they are going to be equal to f of a and g of a. So, by the limit laws, whatever the limit rules we have seen earlier, just like that one would get the continuity of this algebra of the continuous function. So, now if f is a continuous function, g is a continuous function at a, then f g, f plus g, they are continuous functions at a. So, now f of x equal to x is a continuous function for all x in R, that is very simple, limit x goes to a equal to a. So, thus x into x is also a continuous function, therefore, f of x equal to x square is a continuous function. So, in the similar way I can say that f of x equal to x to the power n is also a continuous function for all x in R. Now, therefore, now any polynomial p x is equal to a n x to the power n plus a n minus 1 x to the power n minus 1 up to a 1 x plus a 0. This is a continuous function for all x belongs to R, because this is continuous, this is continuous, this is continuous, all these individually continuous. So, addition of the continuous functions are continuous. So, this is a continuous function on R. Now, any rational function, if I am looking at R x which is equal to p x by q x. Now, where p x and q x are polynomials, that means p x and q x are continuous function for all x in R. So, whenever p of p x by q x we would like to define, this can only be defined when q of x for all those x for which q of x is not equal to 0. So, now R x equal to any rational function p x by q x is continuous wherever it is defined, that is q x is not equal to 0, then this is going to be a continuous function. Any rational function wherever it is defined and the domain of their definition, this is going to be a continuous function. Now, for example, f of x equal to x square plus 1 by x square minus 2 x minus 3. So, now this x square minus this is x plus 1 into x minus 1 into x plus 3. So, this is 3 x, no, x factorize, this is going to be, yeah. So, x minus 3 into x plus 1. So, therefore, this function f is not defined at x equal to minus of 1, this is also not defined at x equal to 3. So, except at those points 3 and minus 1, this function f, this is a continuous function for all x except for 3 and minus 1. Now, so we have shown that the polynomials are continuous function. Now, what about the trigonometric function? So, you see we know that if we consider sin x, then is it continuous? If you sketch the graph of sin x, then you can see that this is a continuous function. It is very easy to convince oneself that this is a continuous function, but how do we prove? Like we want to prove that limit x goes to a, sin x is equal to sin of a. So, one very important alternate test is that we can say that f is continuous at a if and only if limit x goes to a, if and only if limit h goes to 0, f of a plus h is equal to f of a. So, you see if f is continuous, then a plus h, this is going to be equal to f of a. Now, other way around is that if h is, that means you are looking at h belongs to minus delta to delta. Therefore, a plus h, any x if you take in a minus delta to a plus delta, that is going to be look like a plus h for some h is in minus delta to delta. So, this is what we can rewrite the condition to be this. Now, if I apply this alternate condition, then what happened is that if I look at sin x plus h, which is equal to sin x into cos h plus cos x into sin h. Now, as h goes to 0, this is independent of h. So, this is sin s, cos h, cos 0 is 1, then this is 0, therefore, this is equal to sin x. So, therefore, sin x is continuous for every x. Similarly, you can prove that cos x is continuous for every x. Now, tan x is continuous wherever f by g, where g is defined, that means any odd multiple of pi by 2, if you leave out that, tan is going to be continuous. So, all this trigonometric function, now you can talk about the continuity of all this trigonometric function, cotangent function, secant of x, or so wherever they are defined. So, this is going to give you the continuity. Now, what we have seen is that not necessarily limit x goes to a, f of x is equal to f of a. It may not happen, only when the continuity happens, then this is going to be f of a. Now, f of a, I can write it as limit x goes to a, x, a is nothing but this thing. So, here what we are saying, in other words, that if f is continuous at a, then we are in a sense interchanging the limit and the function. That is what the continuity is saying. Interchanging means first you take the limit, then apply the function to that, or you apply the function on the x, then you apply the limit. So, you are interchanging the function and the limit. So, is in general we can do that if f is continuous at a. So, this question we can ask ourselves, that suppose I have a function f and g, and I have a composite function limit x goes to a, f composed with g x, which is equal to f of g x, is this equal to f of, can I bring the limit inside this f? Can I interchange this limit? That is the question what one can ask. Now, the one theorem which would be pretty useful for us to answer this question is that if f is continuous at b and limit of g x, x goes to a is equal to b. F is continuous at b, limit of g x, x goes to a is equal to b, then limit of x goes to a, f of g x is equal to, f is a continuous function which is at b, then this is going to be equal to f of b, which is again f of limit of x goes to a g x. So, now in order to interchange, what we are saying, the assuming the continuity of f at b and the limit of x goes to a g of x is equal to b. So, the proof is that we want to show that for epsilon positive there exists a delta greater than 0, such that f of g of x minus f of b, this is less than epsilon whenever mod of x minus of a is less than delta. Now, from the continuity of f at b, f is continuous at b. Therefore, for this given epsilon there exists a delta 1, the continuity means the limit is going to be f of b. Now, this is if I take a y minus b is less than delta 1, then by the continuity of f at b, this is f of y minus f of b is less than epsilon, because that means limit y goes to b, f of y, this is equal to f of b by the continuity. So, now I have got a delta 1 from the continuity of now also we had been given that limit of g x goes to a is equal to b, right. Now, if I want to apply the definition of the limit, this is true, we are taking the epsilon is our thing. If anybody gives us any epsilon, we must find a delta. So, now the epsilon what we are considering is that suppose we take this delta 1 what has appeared here. For this delta 1 which is a positive number. Now, for this delta 1 we are going to get another delta positive, such that whenever x lies between a minus delta to a plus delta, then g of x minus of b is less than delta 1, right. Therefore, you combine these two, now I take this delta, I take my x to be x minus of a is less than delta. This will imply g of x minus of b is less than delta 1. Now, I take g of x to be equal to y. So, therefore, this is equal to y, therefore, y minus b less than delta 1 will imply f of y, which is f of g of x minus f of b modulus is less than epsilon. That is what you want to prove. Okay, so, then the proof is easy for the composition function. If g is a continuous function at a and f is continuous at g of a, you know, if in order to define that the range of g has to be in the domain of f in order to define the composite function. So, if g is continuous at a and f is continuous at g of a, then the composite function f compose of g is continuous at a. That means, what we want to show is that limit f composed with g x goes to a should be f composed with g of a. Now, what we have given x goes to a, g of x equal to g of a, because g is continuous at a. F is continuous at g a. From the previous theorem, we have limit x goes to a f composed with g x, which is equal to limit x goes to a f of g of x. Now, previous theorem says that if f is continuous at g a b, then we can interchange f and the limit. So, once we do that, we have f, we can take the limit inside. So, this is x goes to a g of x, that is equal to g of a, which is nothing but f composed with g at a. So, this if f and g are function and g is continuous at a and f is continuous at g of a, then f composed of g is continuous at a. Okay. So, now till now what we have discussed about the continuity of a function at a particular point at the point. Now, we can talk of the continuity of the function on a set. This is simply is that if f is continuous for every point of that set, then we say that f is continuous on that set. That means, if let us say f is a function from D to R and E is any subset of R, we say that f is continuous on E if f is continuous at every x belongs to E. It can happen that we have seen function that f is defined everywhere on the domain. Suppose for example, indicator function of 0 1, then there are some subset in which f is continuous. For all x belongs to the, suppose you can define f, I will come to that in a moment, it is there. So, we call A to be the set of continuity of f if f is continuous at every point of A, and we can define the set of discontinuity of f, that A is a subset of the domain D, and we say that A is a set of discontinuity of f if f is discontinuous, f is not continuous at every point of that set. So, let us see the example. Suppose f of x equal to sin x, then the set of continuity of f is R. Now, if I define f of x equal to 1, if x is in closed interval 0 1 and 0 otherwise, then what is the set of continuity? You see, so this is your function. Now, if your x is greater than 1, all these values are 0. So, f is continuous of every a greater than 1. Similarly, if your a is less than 0, then f is continuous, it takes the value 0. So, f is continuous at a less than 0. Now, in the 0 1, we have seen that f is continuous in the open interval 0 1. Now, at the end point 0 and 1, we have seen that f is not continuous at 0 and not continuous at 1. So, now the set of continuity of f in this case, it is going to be the entire real line except the point 0 and 1. So, one would see some very interesting behavior of the continuous function. Now, naturally, continuous function intuitively is the function where I can draw the function without lifting the pen very intuitively. I understand that, that is what the precise meaning what we had given, that limit of f of x, x goes to a is equal to f of a, and with the epsilon delta definition. So, now suppose you are drawing a function, a continuous function, let us say this is a continuous function. So, you can see that at this point the value is being taken to be positive, this is a positive one. Now, I can definitely find an interval in which the f is going to be positive. Otherwise, you see, the point is that in order to reach this, because it is a continuous function, without lifting the pen means I have to travel with some positive number to reach there. Similarly, on this side, I can't go to it from positive, suddenly the interval I can be negative, whereas vis-a-vis if I want to look at this, suppose this is the function, and then I define another function to be here, which are negative, suppose this is 1. So, this function is f of x equal to 1 if x is lesser equal to 1, equal to minus 1 if x is greater than 1. So, here it is positive, but now on anything from this side, this is going to be negative, but we know that this function is not continuous, because if I take the right hand limit, then I am going to get the 1 plus limit f of x, x goes to 1 plus is going to be negative 1, whereas 1 minus limit left hand limit is going to be 1. So, f is not continuous at 1, but in the case of the continuity, it is intuitively that if it is positive, then there will definitely be some small neighborhood, however small it is, this is going to be, the f will take positive value in that neighborhood of that point. So, okay, so that is what it says. Suppose f of x, f of c is positive, f is a continuous function and c is lying between in some interval, open interval a b, then there exists a delta greater than 0 such that f of x is positive for every x belongs to that neighborhood c minus delta to c plus delta. Here it is your c, then if it is taking the positive value here, then you can get this. Suppose your function is like this, or you can go like this. So, however small, but you can always find a delta such that f is going to take a positive value in that neighborhood, and not necessarily it can take in that neighborhood. You see, it can have this, suppose this is the point, I mean it can varies with the small variation, not necessarily it has to increase or decrease, it can varies, but it has to be positive. So, the proof is now f is continuous at c, which means what we want to see, that if in a neighborhood, if it is greater than some positive number, we will be done. Now, you take epsilon to be f c by 2. So, epsilon is positive because f c is positive. So, therefore, there exists a delta for this epsilon such that whenever x lies between c minus delta to c plus delta, f mod of f of x minus f of c is less than epsilon, that is f c by 2. In other words, I can write that minus of f c by 2 is less than f of x minus f of c, which is less than f c by 2. So, now for this delta in for this x in this neighborhood of c minus delta to c plus delta, here from this inequality, what I get, that f of x is greater than f of c minus f c by 2, which is equal to f c by 2. Now, f c is positive. So, f c by 2 is. So, in this neighborhood c minus delta to c plus delta, f of x is positive. So, if f c is big greater than 0, f is a continuous function, then there will be a neighborhood around c in which f has to take positive value. Similarly, if f of c is strictly less than 0, which takes negative value, then it cannot take the negative value suddenly, it will definitely will take the negative value in the neighborhood of that point c, whether if it is positive. But the same thing we can't say about 0. For example, if I have this function which is a continuous function, this is 0 here, but no other value in that neighborhood is 0. But if it is positive, then definitely we are going to get a neighborhood in which this is going to be positive, or negative, we are going to get a neighborhood in which f is negative. Okay, so, now now it is f is such a function that now f of a is taking a negative value and f is a continuous function, and at b this is going to take the positive value. Then you know this is a continuous function. Now, if I try to go whatever way I want to reach, I am not willing, I am not allowed to lift my pen. That means, I have to cross this x axis. That means, f is going to take the value of 0 somewhere between a and b, otherwise without crossing the x axis I cannot reach f of b, which is a positive number. So, I have to cross through 0. That is what is the very important theorem. Proof I will try to explain. So, So, now you take the set A belongs to closed interval a b such that f of x is less or equal to 0. Now, you can see that a belongs to small a, this belongs to a because f of a is strictly less than 0, therefore, a is non-empty. Now, this a is contained in closed interval a b, therefore, it is bounded. So, least upper bound will exist, call that least upper bound to be C. So, then there are three possibilities: f of c is bigger than 0, f of c is less than 0, or f of c is equal to 0. Now, if f of c is greater than 0, what we have shown is that there exists an interval c minus delta and c plus delta, in which f is taking the value to be greater than 0. Now, you see c is the least upper bound, c is the least upper bound. So, nothing below c is going can be an upper bound for that, right, and this is going to contradict this. Similarly, if f is less, f of c is less than 0, then you will get the contradiction, and therefore, what you have left with is that f of c has to be equal to 0. Okay. So, now which is very important theorem of this, which is a very interesting theorem also, what precisely what we are saying in the, if it is negative positive, then it has to go through 0. So, now it says that if f is a continuous function on a closed interval a b, there exist x 1 and x 2 which belongs to closed interval a b such that f of x 1 is not equal to f of x 2, they are different, f of x 1 and f of x 2. Then suppose your f of x 1 is here and f of x 2 is here. Now, this is your function. Now, there can be many numbers. So, alpha, suppose in this case let us say x 1 is greater than f of x 2. Now, so now does there exist a y? Here it says that suppose you take alpha here, then there will be a correspondence y. That is precisely what in case if this is positive, this is negative, then we know that there has to be a point y which is going to be that will take alpha to be 0, then it happens. So, now what it says is that any number you take between f of x 1 and f of x 2, then there is a pre-image, there is a c such that f of c is going to be equal to that number y. So, if we assume the previous theorem, then let us say that f of x 1 is strictly less than f of x 2. Now, define g x equal to f of x minus of that given y, y is been between f of x 1 to f of x 2. Then obviously, g is a continuous function, g is going to be a continuous function because this is a continuous function, constant function y is a continuous function, therefore, g is a continuous function. Now, g of x 1 is equal to f of x 1 minus y, and y you have taken between which is bigger than f of x 1. Therefore, f of x 1 minus of y is going to be less than 0. So, you have a point g is a continuous function which is again defined on the closed interval a b, and g of x 1 is less than 0. Similarly, if we look at g of x 2 which is equal to f of x 2 minus of y. Now, y is less than f of x 2, therefore, f of x 2 minus of y is greater than 0. So, for this g by the previous theorem, on one point at x 1 it is taking the value negative and at x 2 it is taking the value positive. Therefore, there is going to exist one point between x 1 and x 2 where the g is going to take the value 0. Okay. So, that is g equal to 0 means there exists a c such that g c is equal to 0. G c is equal to 0 means f of c minus of y is equal to 0. Therefore, f of c is equal to f of y. Now, let us see some beautiful application of this theorem. Now, let us look at the polynomial x to the power 6 minus 8 x to the power 5 plus 2 x cube plus x square plus 1. Now, do we know that does it have a real root or not? Given a polynomial, we do not know. I mean, we will see that of course, every odd polynomial this is going to have a real root, but this is again an application of this theorem what we will see. Now, for this particular one, so we had been given with this polynomial. Now, we are wondering whether it is going to have a real root or not. I mean, if we can factorize, then that is fine, but we know that how hard it is going to factorize. Sometimes you may not be able to factorize in this. So, now clearly being a polynomial f is a continuous function. Now, f of 0 is equal to 1 which is positive, and f of 1 which is equal to minus 1 which is negative. So, by intermediate value theorem there will exist one point between 0 and 1 which would be equal to 0. Similarly, what we can see that look at cos x equal to x square, does it have a solution in real line? So, with the if you sketch the curve, then you are going to see that actually there it is going to cross at some point, and analytically you can prove that. You consider the function x square minus cos x. Now, you look at this is a continuous function, being this is a polynomial, this is a trigonometric function. So, this is a continuous function, and so f of 0 is negative 1 and f of 1 is equal to positive. So, intermediate value theorem will tell you that this is going to be, there will be a point which is going to be 0. Okay, thank you. So, we will continue with some more application of the intermediate value theorem in the next lecture.